let f of f be the n-dimensional Fourier transform of f of x, where f and x are n-dimensional vectors. We are looking for the n-dimensional Fourier transform of f of ax, where A is a matrix and it's from Rn to Rn. So it's a linear coordinate transformation from here to here. Now let's start writing the Fourier transform equation for f of ax. So this is equal to the integral over Rn of f of ax times e to the minus 2 pi I times f1 x1 plus f2 x2 plus dot 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 to fn xn times dx. Here dx is actually dx1, dx2, dxn, the multiplication, and f1, f2, fn are the elements of the vector f, and similarly this is the vector x. So this summation at the exponents is actually f dotted with the vector x. Now let's do a simple coordinate transformation. Let the vector y equals ax. Then dy is something times dx. This dx was dx1 times dx2 times dxn, and this dy was dy1, dy2 times dyn. So this is a hyperdimensional volume, and this is the hyperdimensional volume after the transformation A. So the scaling factor here should be the determinant of A. So instead of dx, we can write dy over the determinant of A. Now let's write the integral again. Dy over the absolute value of the determinant of A. This is because if the determinant is positive, we should keep the boundaries of the integral as they are. However, if the determinant is negative, we should change the integral boundaries. So we can just keep the integral boundaries as is and take the absolute value of the determinants. Now times e to the minus 2 pi I f dotted with x. Now instead of x, we can write from here A inverse times y. And this is a dot product over here. Now this is equal to. Now what we should try to do is get something similar to the usual Fourier transform formula. So since we are integrating over y, we are looking for something that's y over here, but we have something that's f. So we should have a closer look at here. So f dot A inverse y is actually equal to f Hermitian transpose A inverse times y. Which is equal to A inverse Hermitian f Hermitian times y, and this is equal to A inverse Hermitian times f all dotted by y. So now let's replace this expression with this, and we get the following integral: dy over the absolute value of the determinant of a times e to the minus 2 pi I a inverse Hermitian times f dotted with y. Now, this part of the integral is the usual Fourier transform formula, only we have f replaced by this expression. So this whole integral is equal to 1 over the absolute value of the determinant of a times f of a inverse Hermitian f. And remember that we defined f, the big F, over here in the beginning. It was a Fourier transform of f of x. So now let's look at a simpler case. Let's assume that A is orthonormal. This means that the columns of A are orthogonal to each other and they are unit vectors. In this case, the determinant of A is either plus or minus 1. So these are flips or rotations. Also, A inverse, in this case, equals to A Hermitian. So A inverse Hermitian is equal to A itself. And if we replace A inverse Hermitian by A in this formula, for an orthonormal matrix A, the formula becomes 1 over the determinant of A is 1, f of AF. So just f of AF. And actually, this is the same coordinate transformation that we applied in the very beginning to this function.